All right, good afternoon. Thank you for attending our talk. So my name is DeShon. I'm a data lead at Mastercard, specifically within data engineering, within the fraud modeling space. And I'm with Garzia, Mr. ForEach. He will get into why he's called Mr. ForEach later. But we're going to discuss two business cases that exhibit how we've utilized Databricks and their products to help us scale to the petabyte scale. So there's not really any code that we're going to discuss. It's going to be more on the framework on how we were able to achieve scalability within Databricks and also on-prem. Okay, first, disclaimer. I'm not going to talk to it. You can read it. Probably seen it 100 times today. All right, start off with a quote. Everything works until you scale. So in my previous life, we built pipelines in a healthcare company that used straight Python, pandas, whatever. And it worked for us on a smaller scale within healthcare because we had a couple million patients. So those type of pipelines worked for us. And when I came over to Mastercard, my hiring manager, one of the questions that he asked me during the interview was, what's the biggest data set you've ever worked with? Well, a couple 100 million rows, maybe 10 million rows. That's pretty decent size, right? Not a Mastercard. So his response was, when I answered the question, was, that's cute. So that's really, it kind of alludes to the size of data that we use at Mastercard. We're literally on the petabyte scale within our fraud modeling space. So in theory, pipelines at Mastercard, in theory, pipelines will work, but like I said earlier, they won't work when you get to this size of data. So us as engineers, we take the great ideas from the data scientists and we try to help them scale and get a good solution for making models. All right, so here's kind of a high-level framework that we use. We did rip this off from some Databricks guys that we work with. And we added our own touch to it. So scaling has different levels. We're early in our journey to Databricks, and we use this to, like I said, we use this to scale, get us up to speed at that larger scale. So the first level, we're going to start from the bottom up. First level is your storage level. So this is Delta Lake. This makes sure your data is optimized. Does it have partition pruning? Are we utilizing this file skipping? And are we optimizing all the files? So reducing the file count, taking small files, turn them into bigger files. We go up to the next level, code optimization. This is looking at code structure. Are your functions optimized correctly? Are you reducing any shuffles if you're in PySpark, et cetera? Next, level 3, is we're diving deep into the cluster mechanics. So within Databricks, what type of cluster are you using? Are you using a 48XL and maxing those out? Or are you using like a 4XL and not getting anywhere with your job? So looking at core to memory ratio, the hardware specs, AMD versus Intel versus Graviton. And then finally going up to the next level, which is what Mr. ForEach is going to discuss, is utilizing workflows in ForEach. So this is how we automate, how we orchestrate, and be able to build like 2 to 3 years worth of data in a quick amount of time. All right, so let's talk about optimizing the storage layer. This is specifically on-prem. This is not in Databricks. So first, a story. So this is my son. Yes, it's really my son. It's not fake. So in October, I took my family on a trip to Croatia. found out my grandpa years ago is from there, so we wanted to go see where he's from, the village that he's from. It was a really cool trip. Like, my son's 10 years old. Like every 10-year-old that loves soccer, they love Messi. And he wanted to take his Messi jersey to Europe for some unknown reason. I have no clue why he would want to take a Messi jersey into Europe. It's like competing. So when we were prepping for the trip, we were trying to find his Messi jersey. Like every 10-year-old boy or 10-year-old kid, the rooms are a disaster. Can't find anything, nothing's organized. So the problem we ran into is trying to find his Messi jersey. Where the hell is this thing at? So we went through his entire dresser, went through every drawer, touched every piece of clothing, and eventually found his jersey. So our solution, and this is a real solution. So my house is like decked out with cubes. My wife's an industrial engineer, so this is like the bread and butter for industrial engineering. So when we got back from Croatia, we took his dresser out and put in these cubes. We have the cubes labeled for what needs to go inside each cube. He has his socks, he has his jerseys, he has his jiu-jitsu gis, he has his shorts, school uniform, etc. And then we condensed everything together, so he's not like he has his Messi Argentina jersey in one, and we have a Messi Miami jersey in another one, so all his jerseys are in one bucket. So that was our solution. Made his life a lot easier. He loves it. It was a good solution, like I said. My wife, I have my own set of cubes. She has her own set of cubes. Our pantry has a set of cubes. So why does this matter? And like, why does this matter? Why does Croatia matter? This is basically the premise of Delta Lake, right? So what is Delta Lake? It's that storage layer. It organizes your data for you. You have partitions. You have partitions that it organizes, reduces the file counts, and allows you to read your data faster, to find that Messi jersey somewhere inside your HDFS location. So it takes the Parquet files, organizes files based off the columns that you specify, so for like Z ordering, and which Z orderings, for those that don't know, is just the method that you use to organize your data to enable file skipping. Typically you want to, what we do, we want to Z order by the columns that we're filtering on. And then we have file compaction. So this is consolidating all those files into a big file. So your query doesn't have to search every single small file. And both of these together, utilizing utilizing Delta Lake can help you increase your query performance. So going back to the dresser example, think of having, so going back to the dresser example, think of having 2 cubes of shirts. If we want to compact, if we compact both of those into a bigger cube, then we can find the jersey rather than searching through a bunch of different other cubes, right? Okay, so how we applied cubes to Mastercard. So kind of preface this a little bit. We have a transaction feature table. This table is a massive table, like it's tens of petabytes large. And it comes from the real-time stream. This table contains model features, transaction data elements that we use, scores for all the type of models that we have in production. And it's a very rich table that we can use for many different things. So a couple examples that we use this table for is model diagnostics. So when a model, trying to determine why a model is doing what it's doing, like doing SHAP on a model. Model validation, when the model goes into production, and then same thing with features. If once a feature goes into production, is it calculating correctly? And then proactive monitoring of features and models, so determine if there's any drift or anything like that. So this table gets populated, like I said, from the real-time stream using Kafka and it has some orchestration that pulls all the data into a daily partition, and then they use Spark to move that partition from one HDFS location for the staging to the final HDFS location that we would consume it from. So, similar to my son's dresser, this table was very difficult to query and find anything that we needed to. So for example, if we wanted to find a customer transaction on the model score that their transactions had, it would take a significantly long period of time to query that. And really, even less than, like we couldn't query less than a day. Like it would crash if you tried to just query a day, let alone like more than a day. So the problem we faced is each day became a partition. Full history, we have multiple years, I think it was like 3 years of data that this table held. So you have hundreds of partitions. And then, so you have hundreds of partitions because it went multi-years. So this got big and messy really, really quick. With full history, the table's on the multi-petabyte size. And with numerous small files, because there was no optimization at that time, and that caused major query performance and degradation. Now comparing this to my son's dresser, we already said that. So yeah, we'll move on. Let's see. Okay, so our solution is to use Delta Lake to organize and optimize the transaction table. So in order to optimize our query performance, we Z-ordered the tables on the filter columns. So it'd be like count range, the country, the date, and then optimize on all the partitions in the table to compact everything down. So once done, the results that we had, we get a 70% reduction in file count and physical storage. So it went from tens of petabytes down to, I think it was less than 10 petabytes. And then 80% reduction, or sorry, 80% increase in the query performance. So how we did this, installing Delta on-prem. So you had to get the jar files from delta.io, I believe is the site. So we use Delta Core jar file and the Delta Storage jar file. And then we set, within our Spark config, set the three, that does not work. Set the three configs to pointing to where the jar files lived. And then, like I said earlier, we Z-ordered on our filter, most common filtered columns, so it'd be date, country code, and account range. Some of the learning opportunities that we had were storage for time travel. We do not use time travel. We vacuum everything to 0. We can quickly recreate a lot of the tables that we build. So we didn't see a benefit in time travel that would outweigh the amount of storage that it would take. And then Spark version limitations. So this matrix here, if you can see, it's kind of dark. So this matrix is Delta Lake version by Apache Spark version. So you have to match your Apache Spark to determine which version of Delta Lake you need. Unfortunately, we're on Spark 3.3, so we were only able to get like Delta 2. So we cannot use liquid clustering or any of the fancy new functionality that's out right now. And lastly is getting that paradigm shift to have the organization-wide use Delta Lake and buy into getting queries more performant. I will pass it off to Mr. ForEach.
Okay, I hope everybody can hear me okay. So the big story here is 9 months of computation in 2 days. This is kind of how we sell Databricks. The keynote speaking this morning was actually really interesting. You know, Databricks is really big on this, hey, we're open source first, we're open source first. But the reality is most of us are using Databricks until you hear a story about us using Hadoop. So what's really nice is that we could take some of these learnings from Databricks, apply them to Hadoop. But we also got this really nice like lift and shift. So the story here we're going to talk about is kind of our journey, basically our first project into Databricks and kind of where we landed with some of these design patterns. Okay, this is a long quote. It sounds like a quote that comes out of corporate. It's been scrubbed and cleaned, and it looks like it's something that could be potentially put on a website for the ForEach team at Databricks. So here we say the ForEach operator is integral to our workflow patterns. It goes on and talks about creating these really simple patterns. And the reality is, when we started to run our pipelines, if you haven't realized yet, Databricks is it's a data company, they're data first. And so you get these notes from the product manager going, hey, you're breaking records. Like, we've never seen somebody use ForEach so many times in a workflow, the amount of data you're processing. And so they reached out and they asked us questions about how's it scaling, how's it working. And we had some really great conversations, but it's a little frightening, somebody that's coming to Databricks and you're breaking records. So we want to share like that design pattern that they reached out to us. And I'm told at some point we're supposed to get like ForEach shirts. But I haven't seen it yet, but I'm waiting for it. And anyways, because of this quote, Brandon, my manager, calls me Mr. ForEach. So this is the objectives that I want to cover for you guys. First, we're going to talk about the business case. You know, 9 months is a long time. And if anybody's been on Hadoop, it's slow, but it's not that slow, right? So what exactly are we doing that's requiring this much computation? So we want to kind of create that insight. We want to talk about the technical challenge, like why we chose this approach. And then we're going to talk about a quick note about code optimization and cluster tuning. Learn from me. And then we'll talk about the ForEach and get into a little bit of details. This really only works if you have parameters, and so I'm going to spend a little bit of time digging into the parameters. Okay, so let's motivate the business case. On the left is kind of a very crude graph network. What we have here are cards, and we have merchants, and we have cards that are visiting merchants. And once you do it enough times, you start to build this relationship. You can sort of say, hey, these merchants are related to one another through these cards. And you start to build like kind of a network and start to understand how these graphs and edges work. Once we have that, we sort of have this credit card that has a bit of a history associated with it. So in this case, maybe credit card 1 has visited merchant 4 and merchant 5. Now what we're doing here at Mastercard is saying like, look, over time, these networks have kind of like an energy to them. They have an evolution to them. And you can actually kind of create this what's like called a generative network, right? And what's really cool about this generative network is that you can sort of, as if you kind of imagine like the ghost typing that you see in a VS Code, you can kind of predict the characters that are coming. And so what we're trying to do here is say, hey, we can glean a lot of useful information by understanding how these networks are growing, how cards are interacting, and we can start to create these like scores that we can feed into our model. And so the intent here is to sort of introduce this kind of like, graphical generative modeling into our fraud detections. And the thing that caught me off guard, I've really only been at Mastercard for a short amount of time, is just the amount of like intellectual power trying to figure out how to make our networks evolve and become stronger. And so that's kind of the intuition there. Again, I'm not a data scientist, so don't run off and quote me on some of this stuff. But what do you get? Like this, did you get this like very hard technical challenge, right? Basically, you just have loads of matrix multiplications taking place, along with some conditional statements. And when you look at your Spark metrics, it's basically 100% utilization. So in this sense, you just really have this like CPU bound issue. Like you just need to get as many cores as you can get going. So what makes this challenge particularly difficult is we have to do this over time. So just think going back like multiple years, all the transactions around the world and just almost replaying it. And you're building up this graphical network. You're sort of seeing how it evolves over time. You're creating this generative of predictions and scores that you can then feed into a fraud model. And so we have to do this across the world over time. And so Brandon alluded to it. I mean, we have on-premise Hadoop, but it's a shared service. It's massive. And if you were to sort of say, hey, I want to do this in a very sequential manner, like I'll just do a little bit now, I'll do the next chunk and the next chunk and the next chunk, you end up getting something that like we forecasted out to be almost like a 9-month effort. And so this sort of almost sells itself as like why these elastic computes have, become so powerful. But that's not the thing I wanted to talk about. When Brandon pitched me like, hey, do you want to talk at Databricks? The only thing I really wanted to talk about was ForEach. So we're going to jump into that. But before we talk about that, this is not really a joke. We actually have some senior managers here. Like one time I went for a walk. Early on, we were trying to figure out how to use the Databricks. I went for a walk, and he swings by and sees me walking. He's like, hey, shouldn't you be spending more money at Databricks? I mean, so as we're scaling, we are, we have to pay for all this, kind of in this variable manner. And so the big lesson early on that we learned is that we need to like figure out how to optimize cheaply and quickly, and really know these tools. And so we kind of created this like what we call like an evidence-based optimization framework. And the intent here is to say, look, we don't really know how all these things are going to work, right? So Brandon just kind of like rattled through and said, hey, what's the impact of Graviton versus using Intel versus AMD? What's the difference between using like a lot of small machines versus big machines? And so you can sort of envision this scientific method of just saying, I'm going to create a hypothesis, I want to test that hypothesis, and I'm going to capture the results. And since we work for a data science org, they basically don't. They like the scientific approach, right? They want to see the evidence. They want to understand why. And so one of the big learnings we got here is, since this is a CPU-bound issue, you're actually better off using smaller machines. And so we sort of said, hey, we're going to create these like micro army of small machines that just start cranking out matrix math. So you're starting to get a sense of how we broke some records, right? Like we got all these worldwide transactions. We're trying to build this graphical network over time. And we got an army of small machines that are going to do the mathematics. And so this is like fundamentally what our pipeline looks like. What we really want to do is this parallelization. And when you think about parallelization, you want to get away from the sequential, but it's like, how do you approach the parallelization? And this can be multiple approaches that you could take, One is you could say, I'm going to Spark, I'm going to, have one massive cluster and, submit a bunch of Spark jobs. But there's a lot of guardrails, right? They're not going to let me go off and build a 2,000 machine cluster and try to do this. And so the approach we came up with was, let's just have a bunch of clusters running in parallel. So each one of these clusters have about 100 machines in them. Let's just say we've had conversations about what the AWS inventory looks like. So I actually kind of know, like in my region, when I say for these small machines, how many are available, and we'll just go, we generally just grab like 60 or 70% of them and try to leave a little bit for the rest of the regions. So when we talk about scaling, this is the kind of effort we were talking about. And so when the product team reaches out and says, this is the most ForEaches I've ever seen in the pipeline, and how you guys cranking out so much, it's because we had to parallelize using clusters, as opposed to sort of keeping them one cluster and using that way. So on the very far right, we have, I assume like maybe everybody kind of knows what the workflows are. So this is our workflow. Basically, we start with this like notion of a job parameters. And the first thing we're going to put in there is this like pipeline configuration notebook. And what we want to do here is sort of break the dependencies between the notebooks that are going to run in ForEach and the job parameters. So I could say something like run 3 years of data, but the notebooks themselves might be like 1 week of data. And we'll talk a little bit more about some of that motivation, but the intent here is to sort of keep this relationship with our data science very close. You know, when you start talking about these very like complex features, and if something goes awry, like I don't want to have to give them like this decomposed view of what we've done and stripped it apart. So we kind of keep these notebooks nice and fat. And I got more pictures to talk about what's going on here. And then we're going to pass basically kind of a list of dictionaries to these ForEach, and then they're going to just start iterating one after the other. So I'm going to go through one step at a time here, but just again, job parameters, we're passing information to this kind of configuration notebook. The configuration notebook's responsibility is to split up all these lists, and they're going to pass them to the ForEach. And each ForEach has its own cluster, and it's going to start cycle through. So the parameters is the key to all this. In fact, I think without the parameters, Databricks would be kind of like a really bad solution in a lot of ways. So, but it's a little difficult. So what I wanted to do is take a little bit of time and like walk through this, like how we wired all this up. So the first thing first is just to give some context. We have a notebook and the ForEach. So within that ForEach, it's going to call this notebook. Atop of the notebook are these parameters. And if you haven't used them, the big idea is like if you've ever written Python code, anything that's kind of global, you know, you always start with the globals. We're just going to take all those globals and we're going to move them up into these parameters. And what's nice about this is then the data scientists can like make the changes. And now we have this kind of like common interface layer. And so the way you do this is DB utils. There's widgets for like creating them and then DB utils to get. So it's a little tricky at first if you haven't done this yet. You can actually leave the create and the get in the same notebook. You don't have to comment it out. There's sort of this magical something going on behind the scenes when the workflow runs. So we're going to start trying to decompose this a little bit. So there's many parameters. First we talked about the notebook level parameters. Now we're going to talk about the job parameters. So on the left side, what we're talking about here is that the job parameters, we're going to treat this like a UX layer. We're going to basically say, hey, I want another engineer to run this. Here's a very simple UI. Go fill this out. And so what I do here is just keep everything job underscore to sort of say, hey, these are my job parameters. So I can start to distinguish between what's a job parameter and what's a notebook. Once we do that decoupling, we get into the configuration notebook. And its only job is to take this sort of job parameters and turn into what the workbook needs. And the way it's going to do that, I'll have it in the next one, is you're going to get to this task. So now we have notebook parameters, we have job parameters associated with the workflows, and now we're getting into task level parameters. And so you sort of have to keep all this together. What this looks like now is, on the left is what's really coming out of this configuration notebook. What we're going to do is for each one of these clusters, we're going to pass in these parameters. And so this sets up like a very like nice design pattern that we sort of just keep using again and again and again, where we sort of like, we're trying to keep things simple. So all of our data scientists, when they're doing this like range-based approach, if you look at their notebooks, they have this kind of ForEach. And so we just kind of rip out that ForEach and now we're putting it into the workflow. And so the notebook themselves are getting simpler, and the workflow is kind of also looking pretty simple, but it just requires getting these parameters right. And so now we've created these like task level inputs that we're going to send to our ForEach. And just a real quick aside on the ForEach, like I came from a GCP shop, and so when I started working with this, the ForEach is actually kind of like a really clever implementation. You can sort of see how Databricks thinks. You can see like I want to, because in some sense it's like an anti-pattern. Like the whole point of a DAG is sort of this notion of a direct acyclical graph, which means everything just moves one way. Here we're talking about building these workflows. They're going to stop, and it's going to basically just cycle on itself. And so there's, like, if you study Python, there's sort of this notion of like the Zen of Python, right? Sometimes practicality beats purity. And I think the for each operator does that. I think it's just a really clever implementation. You can kind of see how Databricks is sort of thinking like, hey, these are our users, here's the most common things you're gonna see, and we're gonna kind of expose that. So then this is the last step, which is just the for each is then passing the dictionary into the notebook. And it's just going to do this right, one after the other, one after the other. So this view is surprisingly powerful. If you try to do something like this in the Airflow, where you say, hey, like, I want to run many pipelines in a row, you end up having to like call each one of them separately. But here you get this observability like out of the gates. And so you can sit there, go into this for each, and you can see every single one that's run. And when you do that, you get this view. And early on when we were kind of doing some of our optimization, we actually turned this into our experimentation. We got multiple clusters running, and so we can sort of say, okay, these are gonna use this kind of, this machine, we'll use this machine, we'll use this machine. And we can see the impact over time, right? Because volume of Mastercard sort of grows over time. And so when you sort of spread out the values across these multiple clusters and you run them in a for each loop, you can get this observability view and you can see like, how is this performing over time? And if you started seeing these kind of big jumps, you could say, okay, I need to like tune the cluster again. And so this is like a big, the thing that this is the thing that I came to really appreciate about this like for each operator. So the pros here is the summary view I'm showing here, and then this notion of a Pythonic expectation. When you're designing this great software, you kind of have this like, you want to design for the least amount of surprises, and I think they did a really good job here because it's actually like a lot of challenges, sort of saying, if you got 4 things into that you pass into for each and the second one fails, like what's the behavior that should look like? And so out of the gate, the default behavior is kind of keep it like Python. Second one fails, we're going to stop there. But it's actually really, really powerful because you can also do like concurrencies. You can say, I'm going to send in these 4, just do these 4 at once as well. So I don't know, I'm a big fan. I'm waiting for my shirt. I hope I get it soon. But as far as cons, with this design, it's really just managing the compute inventory. This is a sort of a big challenge for us is like, as these things are running, you can just run out of machines at AWS. The current version is static, and then there's this little part where the cluster disk space seems to fill up a little bit faster than you would expect. So it doesn't seem like there's this, like after each for each, there's kind of a little bit of clutter that seems to be moving along, I think. I could be wrong. But our next steps here is just basically try to do this since it's static and move it over to the Python SDK. The Python SDK gives us then the complete flexibility, so we can actually be even smarter. We can sort of interrogate the data, evaluate kind of what we need from a resource perspective, and then design these things dynamically. So that's kind of where we're going in our journey. I think this is on everyone. Be gentle. We're not the Databricks employees that get a lot of training, so we did our best. Hopefully you got something out of this, but be nice if you want to fill out the survey.